Okay, so we're going to build up, we're going to prove a theorem, but we have to have a easy result first. We're going to prove a theorem that we saw already. So if we go up to our examples, we saw that when you mod out by the ideal generated by 11, you actually got a field. You got something a little bit better than a domain. Well, you got something with more structure than a domain. You got a field, so we're able to divide here. We also saw that we modded out by x squared plus 1, we got a field. And we also saw that when you mod out by the ideal x minus 2, you also get a field. It turns out that in each one of these cases, we actually didn't mod out by a prime. I mean, we did, but we modded out by more than prime. We modded out by something maximal. We're going to see that maximal implies prime in general. We've just seen that the reverse direction is not true. We just had that example of a prime ideal which is not maximal. But in this video, we're going to generalize what we saw in that example. We're going to show that when you mod out by a maximal ideal, you get a field. And it's an if and only if as well. But first, we need a lemma. So our lemma is this. Suppose you have a commutative ring, and we have a maximal ideal in R, and we have something not in R, but it's not in the maximal ideal. So, your maximal ideal, R is like here. Your maximal ideal is maybe in green here. So here's your M. And we're going to take some X outside of it. Okay. Then we can look at the ideal generated by X and M. So we're going to look at all multiples of X plus things in M. So R is in R, and then Y is anything in M. We might have better notation for this and write this as sort of the ideal generated by X and M. But M is a set, it's an ideal itself. So it's not just an element, it's like a subset. So this notation is kind of abusive. The better thing is to write that out. Okay. But all we're doing is we're saying, hey, let's look at the smallest ideal that contains M and X. Okay. What we're going to show is that J is in fact an ideal. So this construction makes sense to do. And M is contained in but not equal to J. So there exists R prime in R and Y prime in M such that 1 is XR prime plus Y prime. J is certainly, once we show it's an ideal, it has X in it, right? X is an element of J, and X is not in M. So although it has all of M, it also has more than M. It has this element X. But M is maximal. So if M is maximal, J must be all of R, right? That's the definition of maximal, is if I'm properly contained in something, it must be actually the whole ring. So in particular, J has 1 in it. So 1 will be able to write as a combination of, as an element in J, and that's what elements of J look like. So we'll come back to that. This last part, there's not much going on there. All right, so let's do the main content here is that J is an ideal, so let's prove that. Proof. Well, 0 is X times 0 plus 0, which is in J, right? And all we need here is to note that 0 is in M, as M is an ideal. M is an ideal. And that's what elements in J look like. They look like X times something in R plus something in M. So this is in R, this is in M. All right, so it has 0. Let's do plus now. Let me say like plus. Let's take some XR1 plus Y1 and XR2 plus Y2 in J. Then, when we add them together, we can reorder and then we can factor out the X and associate the Y's. Y1 and Y2 are in M, so their sum is in M. R1 plus R2 is in the ring, so this is X times something in R plus something in M. That's exactly what elements of J look like. And now the last thing we have to do is we have to show it's sort of closed under multiplication by R. So let's take some, I don't know, S in R, and let's take some XR plus Y in J. Then S times XR plus Y is, well, XSR. We're commutative, so we can multiply. When we distribute, we can multiply however we like, plus SY. But SR is, of course, that's an element of R. This is an element of M because Y is in the ideal generated by, well, Y is in the maximal ideal M, and ideals absorb multiplication, so that's also an M. So this guy is in J. Okay, so this tells us that J is an ideal. Since M is maximal, well, since X is in J and X is not in M, well, okay, let me say one more thing before that. Let's notice then that for any Y in M, we can write Y as X times 0 plus Y. That's in J. So M is a subset of J, but X is X times 1 plus 0 is also in J. So M is not equal to J because X is not in M. Okay, so M is properly contained in J. By maximality, J must be equal to all of R. Thus, 1, which is an element of R, it's the multiplicative identity, is in J, so that there exists some R prime in R and Y prime in M with 1 equals XR prime plus Y prime. And that's just what it means to be in J. If you're in J, you look like that. So that's that last part that I told you there wasn't really much content to. Okay, so this video's gone a little bit long, so we'll do the proof that the quotient is a field if and only if the ideal is maximal in the next one.